So by now, hopefully you've built up at least somewhat of an intuition for what I mean when I say the entirety of 3D space you're looking at right now is a stereographic projection of a four-dimensional hypersphere. The reason for going through all the effort to view the 4D sphere in this strange way is that it makes it possible to look at something quaternions are doing up in 4 dimensions down here in 3. Namely, the quaternion multiplication looks like 2 rotations that are, in a sense, perpendicular to and in sync with each other. To understand what I mean by that, let me first show you how quaternion multiplication is an extension of complex multiplication. So, in the complex numbers, just on a 2D plane, if we multiply by I, the effect that this has on any other number is to rotate it 90 degrees, counterclockwise, about the origin. And more generally, any other complex number on this unit circle corresponds to a certain rotation. And the way you can think about that rotation is by imagining grabbing the point at 1 on the right here and moving everything in the only rigid motion possible that puts 1 on that special number. One kind of nice way to represent things here is if I switch the notation for our unit complex number to be written with an angle, where the real part is the cosine of some angle, that gives you the x distance, and the imaginary part is the sine of that angle, that gives you the y distance. So notice as you change this angle, the red dot it corresponds to on the circle is rotating. It ends up that angle away from the horizontal axis. And in fact, it wouldn't be a bad idea to right now play around a little bit with this angle and think about what this looks like on the stereographic projection of the circle, which is just a line as you see on the right here. Because if you understand what rotation looks like there, then it won't seem so crazy when I go up to our 4-dimensional view and I say that multiplication by I, where our view is just restricted to a single circle up on that hypersphere we can't see, looks something like this, and how that's actually a 90-degree rotation. In fact, I can switch our view here also to be in a notation that shows things in terms of angles. So here, as you change that angle, you'll see this strange morphing motion along a line in the x direction, but we can understand that that's actually the stereographic projection of a circle up on the hypersphere. And more concretely, here's what I mean by multiplication acts this way. So what we have in our viewer here are 4 different points. 1, I, -1, which at the moment is at infinity, and -I. And the function being applied to it is to take q1, whatever we've set in that upper left, times that point, and then q2 at the moment is just the number 1, but we'll be changing that in a few minutes. So for example, if you want to see what I times 1 is, change q1 to be I, and notice what f of 1 is. It is now in the point where I used to be. So I times 1 is I, which should make sense. Similarly, if you want to see what I times I is, well, notice what happens to f of I here. It slides off to the point at infinity, which is -1. So this is our applet showing us that I times I is -1. Likewise, if you want to pause here, you can take a moment to think about what I times various other values gives us. Now, one sort of hack that we can do here is if I change q2 in some completely random way, where you don't need to worry too much about what exactly this means, the effect is basically to change our view of the hypersphere so that when we're displaying this circle through 1 and I and -1 and -I, we actually see it as a circle rather than getting projected onto a line. And when we do that, and we multiply by I from the left, maybe it seems a little more reasonable how this is supposed to represent a 90-degree rotation. Or if we shift the notation a bit, how it can represent rotation by any other angle. Now let me set things back to where they were, and let me ask you, what does multiplication by I do to the other quaternions up on the hypersphere, like j and k? Well, take a moment right now to play around. If we display f of j and we display f of k, what happens as you change q1 to be I? Well, what you'll notice is that they rotate 90 degrees about the I-axis. And in fact, if we also pull up -j and -k, and in fact the whole circle passing through j and k, that circle rotates 90 degrees about the x-axis. And one way I like to think about which way it rotates is to take my right hand and point my thumb from the origin, where f of 1 gets projected, to I, and then see which way my fingers curl. The direction they're curling tells me which way that perpendicular circle through j and k gets rotated. And again, if we want, we can do a bit of a hack to see this from a different perspective, effectively projecting from another point on the hypersphere. When we do it like this, We see both circles as actual circles, and as I'm multiplying by I from the left, maybe it makes a little sense how you could describe this as two rotations perpendicular to and in sync with each other. So setting things back to where they were, one property of quaternion multiplication is that order matters. So multiplying by I from the left actually gives a different effect from multiplying from I on the right. So go ahead and try this. Change the value of Q2 from 1 to I, and see if you can tell how that's different from changing the value for Q1 from 1 to I. What you might notice is that almost everything is the same. It's still two rotations perpendicular to and in sync with each other. And in fact, the effect on the circle passing through 1 and I is completely the same. 1 moves to I moves to -1, and so on. The only difference is that the JK circle rotates the other way. You might think of it as obeying a certain left-hand rule now, where you point the thumb of your left hand from 1 to I, and the direction your fingers curl tells you which way that JK circle rotates as it's being multiplied by I from the right. Filling out this picture a little bit more, we could bring in the entire sphere up on that hypersphere that we can't see, passing through I, J, and K, which is something analogous to the equator of a sphere in 2 dimensions that was just in the plane spanned by I and J. And you can notice what happens to that sphere as all of its points get multiplied from the left by I. Now, if this bubbling out feels a little bit weird, consider what happens to the projection of the equator of a sphere in 2 dimensions as you rotate the sphere. As that equator gets tilted out of place, notice that in the stereographic projection in the upper right, that yellow circle looks like it's getting bubbled out, until, for a 90-degree rotation, it actually ends up looking like a line, which is sort of like a circle with infinite radius. Up on the hypersphere, that sphere equator is getting tilted out of place, and after a 90-degree rotation, corresponding to multiplication by I, it's actually in just the right position so that it's projected as a plane. And the reason for that is that one of the points of the sphere is I, right? That's what you see as f of I under the projection here. But as we multiply I times I, you get -1. -1 is at the point at infinity, so the sphere has to pass through the point at infinity, meaning it's a plane. So go ahead and play around with that, see if it feels at least halfway reasonable, multiplying all of the points on the sphere by I from the left, and also see what it looks like to multiply by I from the right. All right, so after looking at all of that, let's think about multiplication by a few other quaternions. Let's say we multiply by J from the left. In this case, the most convenient subsets of that sphere to start looking at include the circle passing through 1 and J, since that just gets rotated, which under our projection looks like this strange morphing, and then to look at the circle perpendicular to that one, passing through I and K. So take a moment to play with that. Multiply just by J from the left, and if you want, just by J from the right, and see if you can build the intuition for what that looks like. Again, maybe you can bring in the entire sphere passing through I, J, and K, and notice what the product does to that sphere as viewed under our projection. And finally, for the sake of completeness, maybe you also want to think about multiplying just by K from either side, where in that case, the most convenient circles to look at are the one passing through 1 and K, and the one perpendicular to that, passing through I and J. Now to think about multiplication from any other quaternion that's not one of our units, I, J, or K, from the left or the right, we might switch our notation to this angle and axis, and change this IJK part here, which you can see with this pink vector stemming from the origin. And then notice, if we pull up our IJK sphere, as we shift the angle here from 0 upwards, basically decreasing the real part, but increasing the imaginary part, again, at 90 degrees, that sphere gets perfectly flattened to a plane, specifically a plane perpendicular to that pink vector. And if you'll notice, as you're doing this, maybe if you're facing that vector from head on, the sphere is also rotating perpendicular to that vector. So there's no two ways about it. Quaternion multiplication is weird to think about because it's a 4-dimensional thing. Our brains can really only see 3 dimensions. But I do think if you play around a little bit more here, you can get a substantive intuition for quaternion multiplication. And if you need, don't be shy about making things really simple. Isolate it down where you're just looking at one point, maybe I, and you're asking yourself, what does it mean to multiply this by, say, j from the left? And notice what that does to I. Maybe ask, what does it mean to multiply it by k from the left? And you notice what that does. And just keep doing this with several different points and see if you can predict before you change the value where it's going to end up. Where the way you can make that prediction is by asking, which two circles should I think about as rotating perpendicular to and in sync with each other?